Hello guys, let's go over how transformers work. Transformers are a type of neural network architecture that has been gaining popularity. They've been used by OpenAI in their language models, by DeepMind for AlphaStar. They're programmed to defeat StarCraft players, and it has been gaining a lot of popularity. Let's go why they've been gaining a lot of popularity. Like transformers were developed first to solve the problem of sequence transduction or neural machine translation. So that means that any task that you get an input sequence and then you want to transform that to an output sequence. That can include speech recognition, text-to-speech transformation, text-to-text. And the reason for that is that whenever you get text to text, you have a sequence at the input and a sequence at the output. So here you can see how that's done. So like the green dots represent a sequence of elements, and the transformer is this sequence to sequence model, and the purple triangles are the sequence that's being transformed to. In order for models, like neural network models, to perform sequence transduction, it's necessary to have some sort of memory. So let's give you an example. Let's say we want to translate the following sentence to another language, let's say French. The Transformers, a Japanese hardcore punk band. The band was formed in 1968 during the height of Japanese music history. In this example, the word band in the second sequence refers to the band in the first sequence, the Transformers, as you can see here. And when you read about the band in the second sentence, you know it's referring to the Transformers band. And that's very important for translation. Not only text to text, text to speech, speech to speech, you will have elements that refer to previous elements in this text, and in order for you to translate correctly, you need to know that information. And so for a model to figure it out whenever it's translating, it needs to have some sort of reference to the past or to other elements in the sentence. In the past, recurrent neural networks and convolutional neural networks have been used to deal with this sort of property. And let's go over why that's the case. So this is a recurrent neural network. A recurrent neural network allows information to persist, and they have loops around there. So as you can see in this image, you have the input that's represented as xt, the recurrent model, the output, and the recurrence happening here, right? So the recurrence allows the information to be kept over steps. So let's see how it works. So this, you have the sequence x0, x1, x2, xt. That's the same as here, x0, x1, x2. Each xi is one part of the sentence, one element of the sentence. So x0 goes to the recurrent network, generates element, and then it rolls to the next model, and then x1 plus the generated element goes through this model and generates the next output. In that way, we can send information from the past to the future through these connections, right? The recurrent neural network will send over the information to the next elements. And that's kind of how it works. Let's take a look at this image to see how it works. So here's the input sentence, je suis un étudiant, and we want to translate that to English. I am a student. So G goes to the first encoder RNN, it passes the information to the second one, and passes to the third one, and then all the information goes to the decoders. And that translates the sentence to "I am a student." In that way, we can gather all the information from all the elements and pass it all to translate. The problem, though, is that when you have long-term dependencies or long sentences. Why is that the case? Because the information is passed from one element to the other through these arrows, and the information will be lost over time. When you have a huge sentence, the information is lost a little bit here, is lost a little bit here, a little bit here, and a little bit here. And then the farther away it is from the first element, the more information is lost. The idea behind it is that you can't pass all the information on every step. Like on each step, you need to encode the information somehow, and you can't keep all the information. So in that way, RNNs can't keep much information. In fact, when the distance is very long, they lose a lot of information. So RNNs don't work that well for long sentences. So one way of solving that was the creation of LSTMs or long short-term term memory neural networks. So the way they do that is to keep some information as important. So let's take a look at how LSTM works. So each cell takes an input. Let's say this is LSTM. It takes the input, the previous cell state, and the output of the previous cell. It manipulates it and generates a new cell state and an output. So the idea behind it is that we also get the previous cell state as well as the output of the neural network. But so you're basically passing the last cell state as well as the output, so you gather more information, but that doesn't solve the problem completely. So let's go over the problem of LSTMs. So the same problem that happens with RNNs happen with LSTMs. And there are three basic problems with LSTMs and RNNs. So first, the sequential computation doesn't allow for parallelization. What that means is that you have a huge sentence, you can't perform a computation at the end of the sentence and at the beginning at the same time. It needs to be in sequence. There's no explicit modeling of long and short range dependencies. So there's no way to model the dependencies of words within a sentence and the distance. And the distance between positions is linear. What that means is that if I have something that's very far away but it's referring to something back, the distance to send that information is linear. So you might lose that information. So to solve this problem of this distance and these three problems, researchers create something called attention. When translating a sentence, I can pay specific attention to a word in the past that I'm trying to translate, and that's the idea behind attention. So the the key idea here behind attention is the key idea behind attention is to figure out which words to look at when translating at a certain step. So when I'm translating "Je suis étudiant" and translating "I am a student," when I get the word "I," the first step of that decoding, I know that "je" is like the most important word in that sentence to look at. So at each step, I have a score of how important the word in the first sentence is to translate the next sentence. And here you can see that I is like the score of "je" when translating "I" is very, very important. And like here, as you can see, the intensity of the orange color will show how important a word is to translate to the other word. So we're basically creating a matrix of scores for each state compared to the other state. Some of the problems of RNNs are not solved with attention. Attention can help with figuring out where to look at when translating, but it doesn't help with parallelization, right? Because I still need to go step by step. So even with this score added to RNNs, I still can't figure out how to parallelize the work. So how do we solve that? CNNs are an easy way to parallelize and exploit local dependencies. So let's take a look at a famous CNN, WaveNet. I don't know if you guys heard of WaveNet. It was one of the first neural networks that was used to create sounds based on text using a neural network that performed really well. It was a DeepMind model, and it created waves when it was released because it performed so well. So you get the input, and each step will look at a bunch of inputs whenever translating, whenever creating the output. And you can see that whenever creating an output, you don't depend on the previous output. You can calculate any step independent of each other. And not only that, the distance between the output word and any input for a CNN is in the order of log n. That's basically the size of the height that the tree generates. If you look at kind of the intuition behind it, why is log n, is because at each step you're basically getting 2 or whatever and going to 1, right? It's kind of that the idea. You can have more than 2 or like 3 and generate 1, but that sort of creates the intuition that you're basically have a tree of size log n, right? And the thing though is that CNNs don't solve the problem of figuring out the dependencies when translating sentences. They can help with parallelization. Attention can help with figuring out a little bit of dependencies. But how do we get to figuring out dependencies and have parallelization? And that's where transformers come on. So you basically join together the two ideas, the CNNs, convolutional neural networks, together with attention models, and you get the transformers. So let's take a look at how transformers work. Let's take a look at transformers. Transformers combine the idea of attention and convolutional neural networks, specifically using self-attention. So self-attention, the idea is that instead of having something global for the whole sentence, each word will have an attention that's specifically to the previous sentence. So a transformer usually combines 6 encoders, 6 decoders, and each encoder is similar to each other and each decoder is similar to each other. An encoder will consist of basically a self-attention and a for neural network, a simple neural network, and like the word will flow through the self-attention first, and then through the feed forward network, and the decoders, the way they work, they have a self-attention as well, encoder decoder attention, and a feed forward. So how does the self-attention work? You can take a look at Jay Alamar's blog post that explains it very well. I will link to all the sources where you can learn a little bit more. But basically, you're calculating a score of each word, like here. Like I has a score, kicked has a score, the has a score compared for that position, and you can basically calculate doing some math. You can go to my blog post to see how each step works, but you're basically calculating how each word in the new sentence compares to each word, how important that is. And it's basically a weighted value, and that's kind of how it works. You can improve on that having a multi-head attention, and the idea behind multi-head attention is that not only is important to know how influential a word is, but there are types of influence. So for example, who kicked the ball is important. So like if you see at the green arrows here, they refer to who, and which word answers the question who more importantly are the ones that have the highest score. And for other questions you have other scores, so you can embed that information. And that's kind of how transformers work. So you're basically combining CNNs with self-attention or even multi-head attention. I'll link to more information down below. If you have any questions, please leave a comment, like or subscribe my channel.